So hello everyone, thanks for your patience. Stratasys D2M Solutions and Texas A&M University of Qatar would like to thank you first of all for joining the webinar, and by the end of it we hope that you will become familiar with the latest 3D printing technologies and applications and have an idea of how educational institutions can leverage 3D printing for the benefit of students and researchers. So my name is Aris Petridis. I will be doing this presentation on behalf of D2M Solutions in Dubai. And towards the end of my presentation, I will hand over the controls to Mr. Yasser Al-Hamidi of Texas A&M University of Qatar. He will be discussing how Texas A&M University has incorporated 3D printing, and he will also elaborate on the different range of programs that involves this technology. And of course, before we end the webinar, we will go ahead and answer some questions. So please feel free to type them in the chat during the presentation. For any question that we'll not be able to answer today, we will make sure to answer them on a one-to-one basis during the following days. So as we progress through our agenda today, we're going to start by investigating how the 3D printing process works, then look through some additive manufacturing applications, where they fit, their benefits, and ultimately how they're used to improve and speed up the manufacturing process. So we will explore the possibilities of going from design to production floor in just a few hours with ultralight assembly aids, jigs and fixtures. We're going to see how we can reduce tooling costs up to 95%, how to increase the performance of parts by combining traditional and additive components, and lastly, we're going to see how to produce production parts quickly using 3D printing. So before we kickstart with our agenda today, let me give you a very brief introduction about D2M Solutions. We have been based in Dubai for the past 5 years now, and our company provides complete end-to-end product development solutions all the way from conceptual design down to final manufacturing of products. We offer a very diverse product portfolio that we usually tailor into packages, into solutions, so as to specifically meet and suit what a company or a university wants to accomplish. So our solutions include software and hardware for reverse engineering, quality control, as well as for CAD, CAM, and CAE. And we finally provide industrial high-performance 3D printers to manufacture the final output with a choice of different thermoplastics and resins that have been developed based on particular industry needs. So in few words, what we strive to do is to improve and optimize the design to manufacturing process, reduce costs whenever possible, and at the same time give the unlimited design freedom to engineering teams and designers to unleash their full potential. And this is very true because 3D printing gives you the ability to think and develop products that otherwise would be impossible with a traditional manufacturing process. So we are the gold reseller of Stratasys industrial 3D printers. We cover the entire Middle East region, along with other countries in North Africa. Our headquarters is in Dubai, and we have strategic reseller partnerships in Greece, in Pakistan, and in Saudi Arabia, ensuring fast and efficient region-wide support for our customers. So moving along on our agenda for today, we will take a look at some 3D printing terminologies first. So what is 3D printing? It's a process of creating physical objects directly from 3D digital data or computer models, usually from one layer at a time, from the bottom up, We also tend to use the terminology additive manufacturing to describe the exact same process of this additive creation layer by layer. And the term additive is used simply because we add material whenever needed instead of subtracting from a block of aluminium, for example, as you would encounter in a typical CNC machining process. So there are 3 steps in the process. The first, during pre-processing, is to export your CAD data into the STL format and use the printer software to calculate the placement of material. During production and printing, the system lays very fine layers of material to build the part from the bottom up, one cross-section at a time, until the final product is achieved. And once the part has been fabricated completely, the final step involves removing the support material, either manually or by just dropping the parts into a bath of detergent if you use water-soluble support. So the 3D printer software what it will do is slice the model into thousands of layers so that it can calculate the tool path of the heads. The system, of course, will automatically add the support material whenever needed, so as to support, angles, overhangs, or undercuts. And finally, you have the ability to choose the option of having a sparse or dense build 3D part. That depends, of course, on the requirements for this specific job, whether it is for strength and durability or for fast build time. So when it comes to printing, Stratasys at the moment offers 2 different technologies. The first is FDM, stands for Fused Deposition Modeling, by which the printer heats the thermoplastic to a semi-liquid state and deposits it in ultra-fine beads along the extrusion path that was calculated in the previous step. Where support or buffering is needed for the part, the 3D printer, the system will deposit a removable material that acts as scaffolding, let's say if we were to use a building construction term. Now, the second technology that Stratasys offers is called PolyJet, by which the printer jets and instantly UV cures tiny droplets of liquid photopolymer. And again, of course, whenever you have overhangs or complex shapes require support, the printer jets a removable gel-like material. So both 3D printing technologies I just talked about use soluble and breakaway support. And of course, the choice of which support to use for a specific part depends, in each case on the part's complexity as well as the model material that was used. So now coming to the application of those technologies we have discussed so far. Today we will focus on the manufacturing applications that are highlighted in the red frame on the right side of the screen. I will give you an overview of how 3D printing can be used for jigs, for fixtures, for manufacturing aids, end-of-arm tooling, injection molding tools, as well as for low volume production, high complexity designs, and customized parts. So firstly, I think it would be a good idea to understand the basic differences between PolyJet and FDM. With PolyJet, you can print parts with very, very fine features that are multi-material and multicolor, and final parts replicate true-to-life parts. On the other hand, with FDM, you can print in a variety of different real thermoplastics, not simulated, that give the best results in terms of accuracy, in terms of durability, and repeatability. which means that if you print 100 parts of the same model, you will always get the same results in terms of accuracy, in terms of material properties, and aesthetics. So let us now go through the various applications that I have prepared for you today. The first is jigs and fixtures. These are rapidly designed, developed, and printed, fit-for-purpose tools, jigs and fixtures. They can be built on-site very, very quickly, up to 90% faster than with, traditional manufacturing methods, and with up to 50% of the cost. So these tools, of course, can be stored digitally and reutilized over and over again using a variety of different real thermoplastic materials that may be chosen based on current needs. So the design freedom that comes with 3D printing can be used to create customized and complex parts on demand, and these jigs and fixtures can be used to hold or to protect or to position other parts. So where does this application best fit? Well, when the design is complex, when we have frequent design changes, and when the operational environment exposes those parts to heavy loads, exposes them to high temperatures or even chemicals. And with our production systems, we are able to print parts that are almost a meter by 60 centimeters in dimensions, with very, very tight tolerances of 130 microns. So what are the benefits of 3D printing jigs and fixtures? Well, you can, of course, improve your efficiency and repeatability, as well as the ergonomics of the shop floor, while at the same time you can reduce cycle time, the labor and assembly, as well as the assembly documentation. So the second application I'm going to cover is injection molding. This application is a perfect fit when the goal is to confirm the design and functionality of the mold and to conduct, of course, product compliance testing. For example, will my final products be UC compliant? Well, we can answer this question easily by printing molds on demand and iterate between revisions until the final result is acquired. So where does this application best fit though? The molding temperatures have to be up to 300 degrees Celsius, and the thermoplastic candidates could be any of those plastics that you see on the lower right side of the screen. So it could be P, PP, PS, ABS, amongst others. So by using 3D printed injection molds, it's possible to create quantities of up to 100 parts to test and be able to see exactly how the final product will look with a size up to 165 cubic centimeters, and all of that in an injection molding machine that uses 200 tons of pressure or less. So the benefits of using PolyJet for injection molds are the cost savings on expensive tooling, as well as a reduction of lead times, and the ability to do quick validation and verification of part performance and final material selection. So the third application that I'm going to cover is end-of-arm tooling using the FDM technology. This application is really great to increase the speed, to increase the accuracy and flexibility of parts, because it allows you to combine traditional and additive components and might be used to decrease the variability and labor costs, while at the same time increasing the throughput of a particular system. So as we go into the best fits of this application, again, as we have the necessary design freedom, we can actually print parts that are highly complex with organic shapes, that are lightweight enough and relatively large in sizes, and that undergo frequent design changes. So what are the benefits? Well, by using 3D printing, you can dramatically reduce the design constraints, as you have virtually no limits in design complexity. And you can also optimize the functionality of arms or robots and create customized tooling for specific purposes. So by using FDM materials, you have a great strength to weight ratio, which is, very well suited for end-of-arm tools. The final application that I'm going to cover is low volume production of parts. This is a very good application and can be used as a pilot production to test the market and get some feedback from the customers before you create the final tooling, as well as bridge to production to allow you to bring your products to the market in low quantities until the metal tooling is designed, has been manufactured, and delivered. So it can be used for full-scale manufacturing, or it could also be used for end-of-life manufacturing for products that have been retired from the market maybe, or even to produce spare parts for after service. So as those parts are held digitally, you pretty much eliminate the need for bulky storage. So low volume additive manufacturing can be used for low volume quantities of up to a few thousand pieces. It allows a great customization of parts and frequent revisions, as these parts can be printed over and over again, and allows for complex designs that would be impossible to produce using a traditional manufacturing process. So what about the benefits? Those include lead time reduction, of course. You no longer need to wait for the metal tooling to be fabricated before you put the product to the market. Everything is held digitally, and actually parts can be optimized for performance as you're flexible enough to do rapid assessments and validations daily, one after the other. So the main advantage, however, of using additive manufacturing for low volume production is the huge reduction in cost by avoiding the need for expensive metal tooling. So before I let Mr. Yasser from Texas A&M University take over and do his presentation, I will only outline some of the major industries that we see gain a lot of benefit from those applications I mentioned. For example, in the medical industry, in the medical sector, we are able to take patient-specific images, make customized medical models for the physicians to be able to do pre-surgical planning, as well as get the tactile feel of the patient's problem or the patient's pathology. So of course these models are fabricated from non-invasive studies of the human anatomy that could be done via CT scanning, MRI, or even 3D ultrasounds, and really allow hospitals to customize. It allows them to enhance and improve the overall realism of their training models that are utilized in the education and the ongoing education of their physicians. So no specialized facilities are required to do that, but yet you can replicate all of those complexities and, more importantly, the medical conditions of patients. You can actually simulate live tissue characteristics with flexible materials and get an unobstructed true-to-life view that a computer model projected on a 2D screen just cannot match. In education, what we do is assist professors and their students to be innovative and do things that would be otherwise impossible. 3D printing allows designers to drive the design process towards innovation by enabling them to efficiently visualize their ideas. So 3D printing delivers a real, let's say, world design and production challenge to a student in the classroom. So by using a 3D printer, the students have the ability to actually hold the output of their work in their hands. And we believe that that simple act alone can turn the disciplines that they are learning every day in the classroom, the design and the prototyping, into something more real and more authentic. And in the end, what we need to do is to prepare the students for you know, the real world, what happens after they graduate. So now I would like to transfer you know, the controls over to Mr. Al-Hamidi from Texas A&M University of Qatar. He will give you his side of the story, how his university is using 3D printing for the past several years, and what they're able to accomplish by using this disruptive technology.
Hello, good afternoon. Sorry, my mic was mute. Thank you, Aris, for your informative presentation. And I will start actually from where you ended up your presentation, talking about how this technology is changing the way we conduct our day-to-day life. In particular, I will be focusing on the education sector. The first slide is basically our facility, the 3D printing facility, which we started building in 2006. And it's actually history. We started from desktop printers, and we ended up with good production printers with a large bed envelope that would allow us to really print a good amount for students. Since we established this facility, actually, the way we really educate our students, it changed dramatically. And I would like to show you how this disruptive technology is really changing the way we educate our engineers at Texas A&M University, and like what Aris mentioned, how to prepare these engineers for the future after graduation, because we would like our students, our engineers, to be able to go and recommend the best manufacturing technology that would really best fit the needs of the industry. Starting from having some of our mechanical engineering students modeling and printing different parts to be used for classroom visualization. Actually, this is also a good print, and before we show you the actual parts that we printed for visualization purposes in the classroom, I'd like to show you that the production printers which we do have with such large envelope allowed us really, especially at the end of the semester where we have rush for doing projects, to print a good number of projects for students. We introduced this technology actually in Texas A&M University at early stages. Once we have the students in their freshman year, they basically take an engineering foundation course where we teach them CAD modeling, and then we ask them to actually we print for them whatever they design. And we can feel it that when they touch and feel the parts which they designed, it is really different. They learn a lot from having these physical parts between their hands rather than just looking at them in basically virtually on the screens. So usually this class, the engineering foundation class, which all engineering disciplines take, you know, we have more than 100 students, and again, to be able to print all of this, as you can see here, we plug a lot of projects in one run actually. So here again, what they learn is basically they can, for example, learn tolerances and how they can have their design rectified according to whatever they see. It's not costly also to go for different design iterations, and as Aris mentioned as well. This is another example for another project which we did for our students, but this project basically I attached here just to show you how really you can come up with an idea and you can CAD model your design, and then you can simply print and test and see how it works. Our using for the 3D printing technology went beyond actually just having our students use it. We use it even to fix some apparatuses in our lab. This is a Stirling engine we use in our heat transfer lab to teach students about this type of engines. And actually the current photo shows that the connection is basically between the engine. This motor is, or this generator is through this rubber pelt. We had some issues with this setup, and we thought it might be a good idea to change to this type of gear mechanism to be able to, and we did this actually. We printed this and it is perfectly working fine with us. For students projects actually also we have from time to time even some competitions we run in 3D printing. This is a good example about how we can use a 3D printing to print real products. This is a quadcopter designed by one of our mechanical engineering students, and his design was really amazing. As you can see here, there are different landing gears actually inside these parts here, which can be remotely controlled. This is exactly shows what I just mentioned, and this is the whole quadcopter. You see, you can just CAD model whatever you would like to design and print and see how it functions and do testing and go for other iteration of your design. For classroom visualization, which I just started with, this is, for example, one of the things which we had our students designed. It's a flat plate heat exchanger. What's good about doing such stuff is basically you get students engaged in the design of these, for example, heat exchanger, and when they get engaged in such design, they have to learn the whole background and theoretical background behind the heat exchangers. This would allow in the classroom to explain ideas, to explain to students, for example, how the heat is transferred from the hot fluid to the cold fluid without having both fluids to mix up with each other. And as you can see here, we have a 3D printed, or sorry, a cross section for the flat plate heat exchanger. Again, this will really help students a lot in the classroom to easily grasp and understand the idea behind heat exchangers. Similar to these heat exchangers, we printed the shell and tube heat exchanger, which is another type of the heat exchangers. Again, this is something can be used for demonstration purposes in the class. Another project in mechanical engineering, something we did, is a variable geometry wing. You know that nowadays there is a hot research about how the airplane wings can be optimized from aerodynamics viewpoint, such that this definitely will result in having a less consumed fuel and would actually cause as well less pollution and less emissions. So some of our mechanical engineering students wanted to test this, and they came up with this design for the variable geometry wing, and this was their proposal. As you can see here, actually they added a good amount of or a good number of degrees of freedom to be able to have the whole wing actually change according to the flight conditions. So according to the flight conditions, there will be different commands that will be sent to different modules here. So you see, for example, this module can rotate in this direction, and actually it can rotate along this pivot point here, or it's clearly shown here. So this is the printed part, and our students try to just test this in our one of the wind tunnels which we do have here. You can see also here in this slide that the whole support for all of these modules can also change the angle. So this is a good example for how students can innovate, can imagine, and can come up with new ideas to test and learn. Moving to maybe chemical engineering, I don't want to have all of my presentation about mechanical engineers. We have chemical engineering also. I forgot to mention that the facility we do have supports our students, support researchers in Texas A&M from all engineering disciplines, and it supports other researchers from other neighboring institutions, in addition to support the community. So we have a community service. If anyone would like to print, we have we do provide help in this regard. We have two researchers from chemical engineering wanted to see how 3D printing can be beneficial in catalysts. And without going into a lot of details in this regard, there are different ways in which you can use different materials in the catalysts. Anyway, they went for a specific type for many reasons beyond the scope of this presentation. They went for something called the monolithic catalyst, and in which they wanted to use 3D printing to create a smart structure for their reactor. So the objective was to design a new structure for monolithic catalyst support, and maybe to optimize this design utilizing the 3D printing capabilities. Their project was motivated from the application which everyone knows about, the catalyst inside the cars. And here actually the reaction inside the catalyst is proportionally related to the surface of the reaction. This is why we came up with this smart structure which really increases the exposure surface between reactants, and that was actually printed in plastic and in metal. This shows that this smart structure, and these are the different parameters for this structure, and that was tested in the lab. And you can see here, this is actually inside one of the chemical engineering labs where we tested the smart structure inside the monolithic catalyst. And you will see towards the end of this tubular reactant, this is whatever we printed using our 3D printers. Another project was done by a researcher from mechanical engineering actually, is about how to improve the engine performance, the car engine performance, by designing a new inlet manifold. And this actually shows how the air goes through the throttle valve to the plenum, and then it goes again through these runners to the cylinders. He came up actually with different designs, and he tested all of these different designs. Actually, the good thing that he did, he tried even to simulate and to do a finite element analysis for all of these designs to be able to finalize the product and to be certain about which product he needs to use as a final product. And for example, this is his design with a center throttle body, and that design was not good for a couple of reasons which I will mention right now. This is actually another view for the same center throttle body, and again the design was a little bit larger to fit under the start part, and actually we figured out that in this design the top runners flow more air than the bottom runners. This is why this design was not a satisfactory design. So he tested another design, which is the tilted side throttle body. This is the throttle body where we control actually the amount of air gets inside the engine, again through this plenum and the runners here. The same, there was an issues with this design, and the main issue was that there's no, again, consistency amongst the flow that comes out of all of these runners. This is another review for the same one, and this is the side throttle body, which apparently was the satisfactory design. As you can see here, this throttle body is not tilted, it's straight, and that was actually the one for which we did this is the whole design, the final design for the whole inlet manifold. And as you can see here, this is for the first runner, and this is for the second runner. And if you can see the numbers here, this gives you an impression about the flow. And this is for the third runner. All of these are finite element simulations, and that was the fourth runner because this is a 4-cylinder engine. As you can see here, if you notice these numbers, it's between 173 and 175, or 178, sorry. There's less than 3% flow difference between the highest and the lowest flowing runners. And so this is very, very important in this regard. We printed this design in our FDM plastic printer, and this shows you how our printer actually, this is what Aris explained about the FDM technology, fuse deposition modeling. Additionally, here we tested so here we apparently this is a plastic part. It cannot be tested for a long time inside the car engine, but this was really good to at least for a short time to test the actual printed part or prototype. Again, very interesting research projects in which we use 3D printing. This is for piezoelectric actuators. This is the piezoelectric tube, and this is the guide. And as you can see, we designed the whole platform with the holders for the sensors, and we 3D printed them. And this helped a lot because the sensors, the proximity sensors used to be able to capture the vibration during motion of this piezoelectric actuator, you know, these needs to be adjusted very accurately. This is why we have here this micrometers. So we used the micrometers, we integrated them with the 3D printed platform. As you can see here, we managed to have these wires neatly connected, and then the researcher actually was ready to conduct his experiment in easy and fast way to be done. Another very good example shows how you can use 3D printing from design to manufacturing is this wheelchair power bar, and this is the concept, the rendering for in the computer, how one of our actually technical lab coordinators envisioned this power bar. So basically this is just to convert a normal manual wheelchair into a motorized wheelchair. And this is the actual printing. We have the covers actually, but we removed the covers here just to show how the whole project was implemented using 3D printing. As you can feel here, that the benefits of 3D printing allow the transformation of the concept from an idea into a tangible functional prototype. So you can really test and investigate the fits and functions of the device, and actually this enables foreseeing how to develop the device further. So this actually what Aris referred to in his last presentation, and unfortunately we have really a good number of collaboration we did with many institutions, but we cannot show all of these projects because of the patenting issues and the IP issues. So this actually we take the MRI or the CT scan, and we build a 3D model, and this is something very interesting to be done for many reasons, like for pre-planning for surgeries. This is, by the way, a kidney with cancer. As you can see here, we were able to model and separate the cancer from the kidney itself. And I would like to show you, this is actually the printed parts, and you can see here really, this is the actual kidney with the cancer here, and you can see how really there is, I mean the actual or the printed really represents the actual kidney. So as I mentioned, this is for rehearsal of surgeries. It can be used for education on kidney anatomy and training for residents inside hospitals. So I think I'm done with my presentation. Hopefully you feel 3D printing, as I try to show in my presentation, that it is really beneficial for education, and it really changed the way we conducted our business. I will give the floor back to Aris.
Thank you, Yasser. That was really educating. It's quite, amazing to see how this technology is used in Texas A&M, and in fact from different disciplines. So as we have a couple of minutes for questions, we're going to answer a couple of ones that came in during our presentations. The first one is from Mohand. It says, your webinar focuses on how additive manufacturing can increase productivity. why should a university be interested in productivity increase when our main scope is education and R&D? That's a very good question. Actually, in recent times, when worldwide competition is making design and productivity innovation, which is a must to be able to compete in the global market, universities, I believe, should be leaders by exposing their students and researchers, of course, in more advanced ways of using these, disruptive technologies, so that in the future they're better and will be prepared to add value to any company that they will work for. So another question that came in was from Mahmoud. He's asking, when does it make sense to use 3D printing for production over traditional manufacturing? That's another good question. I would say that additive manufacturing should be the preferred method and makes absolutely sense when we're talking about a low volume production and short lead times. So obviously the more parts you print, the lower the cost per part, but there is an actual threshold on the actual amount. So this figure is of course different based on each case. So you really need to put down the numbers to figure out what production method you should use for a specific case. That usually has to do with a particular design, on its complexity, on the number of parts, on its size, maybe on its customization and configuration options. So apart from that, lead times we see for tooling also play a very, very crucial role in determining, let's say, which path should be chosen for the production of parts. We have another question from Salim. Is additive manufacturing here to replace traditional manufacturing? I would say no. The additive manufacturing is not replacing, but it's on the contrary complementing the traditional ways of manufacturing, and is actually able to fill the gap of manufacturing complex designs that are probably impossible to do with the traditional method. So it's here to give unlimited freedom to engineers so that they can develop based on creativity and not based on some limitations on the equipment or in the manufacturing process. As I discussed earlier, 3D printing reduces the cost of expensive tooling and virtually allows countless iterations between revisions of the designs so that you can achieve the best possible final design and product in the end. So as I also said before, it can be used for a pilot production to test the waters in the market, or it can be used as a bridge to production, and of course to print some parts, some spare parts on demand, and maybe some products that have been retired from the market as well. So what we strongly believe will happen in the future is that big OEMs will probably stop storing their spare parts physically, but instead what they will do is hold them digitally and print them and ship them on demand. This is what we feel will happen in the near future. Another question is, what CAD software is compatible with Stratasys printers? It comes from Mohammed. Mohammed, any CAD software that can output in an STL format is compatible with the printers. The next question comes from Chandan, asking how many different colors are available. So Chandan, with FDM, you have the option of 9 different colors, depending on, of course, the material that you have chosen. With PolyJet, on the other hand, you are quite more flexible, and the fact that it comes with a creative software really gives you the ability to choose thousands of colors and mixtures that you can really blend to use for your printed parts. Another question from Brian, what are the different materials that we can use? Okay, if we are going to discuss about FDMs, we have real thermoplastics that we usually divide into 3 categories. We have the standard thermoplastics like the standard ABS or ASA. As we go higher in the pyramid, however, we've got the engineering scale thermoplastics with materials like nylon or polycarbonate mixed with ABS. And then we have the high performance materials, which are usually PPSF and ULTEM. For example, ULTEM is a fly-ready material that comes with all the necessary certifications like for fire and for smoke and chemical, and allows it to be fitted directly onto an airplane. So I would say in total we have, if I'm not mistaken, 13 different thermoplastics, which can really produce very strong, very stable and durable parts that will have the same final product mechanical properties, and of course with a low total cost of ownership. Now that was for the FDM side. If we go on the PolyJet side, this technology uses quite different material. It's an acrylic based plastic and elastomer, but it gives a much smoother surface finish and fine details, of course. I would say it's a true-to-life appearance, and simply because you have the ability and freedom to use materials with different properties like clear or flexible to create your own combination. So, for example, if you take a Connex 3 system, you have over 1,000 material options to choose from, and most importantly, you are able to combine all of those in a single part to create, your own colors. Or your own textures, or even your own material properties. So we have plastics like high temperature, we have digital ABS, we have standard plastics like transparent, rigid opaque, we can simulate polypropylene, we have rubber-like, we also have medical materials, and of course we have hundreds of combinations of those. So I believe that was the last question that we have time for us to answer today. We have quite a lot of questions, so what we will do is we'll make sure to do a follow-up with each and every one of you in the following days to answer every question in detail. So I would like to thank everyone who attended. And on behalf of the organizers, Stratasys D2M Solutions, and Texas A&M, and Yasser, thank you, and we wish you a pleasant evening.
Thank you.